Okay, now that we've looked at how to calculate the pH of a weak acid system, let's look at a weak base system. Okay, remembering that a base is going to be anything that can pick up a proton, so it needs to have a lone pair of electrons. So when we add this base to water, we get an equilibrium process taking place, okay, where we form our conjugate acid plus hydroxide. Now, in the case of strong bases, we know the concentration of hydroxide because we can derive that from the concentration of the base itself. But here we can't do that because we know that not every single molecule of base is going to produce a molecule of hydroxide. Only some of them are going to. So how do we tackle this? Well, in a very similar fashion, except instead of talking about a Ka, we talk about Kb. Okay, because we're talking about a base reaction here. Okay, so the Kb is going to be equal to the hydroxide concentration times the concentration of the conjugate acid divided by the concentration of the base. And as usual, we leave water out because this is a heterogeneous equilibrium and the concentration of water is not going to change significantly. Now, just like we saw with the weak acids, there are tables of values of Kb for a variety of different bases out there. Okay, so let's look at a particular situation, and let's look at what happens if we take ammonia and put that in water. Okay, what this should produce is ammonium plus hydroxide. Okay, and the Kb value for this is equal to 1.8 times 10 to the negative fifth, which is going to be equal to the concentration of hydroxide times the concentration of ammonium divided by the concentration of ammonia. Okay, so suppose that we want to calculate the pH of, let's say, 3.50 times 10 to the negative third molar ammonia solution. Okay, and again, we want to calculate that pH. Well, we know that the pH has to come from the hydronium concentration, and hydronium doesn't show up anywhere here in this equation. In fact, we're given hydroxide concentration. But if you go back a couple videos, you'll see that we can go from hydroxide concentration to pH eventually through some transformations, and I'll show those here. Alright, so here's the solution of ammonia that we have. Okay, now I want to rewrite the equation. That way we can create our ice table. Okay, initially our concentration of ammonium is 3.50 times 10 to the negative third. Okay, and initially there's no hydroxide and no ammonium. Over time, we expect that some amount of ammonia is going to be converted to hydroxide and ammonium. Okay, for every mole of ammonia that gets reacted, that's 1 mole of hydroxide and 1 mole of ammonium. Okay, and then at equilibrium, the concentration of ammonia will be 3.50 times 10 to the negative third minus x. The concentration of hydroxide will be x, and the concentration of ammonium will be x. Okay, now all we have to do is take those equilibrium expressions and plug them into our equilibrium equation. Okay, we've already said that Kb for ammonia is 1.8 times 10 to the negative fifth. Okay, at equilibrium, our concentration of hydroxide is going to be equal to X, and our concentration of ammonium will be equal to X, and our concentration of ammonia will be equal to 3.50 times 10 to the negative third minus X. Okay, and at this point, it's just a matter of plugging things into the calculator. So we wind up with 6.30 times 10 to the negative eighth minus 1.8 times 10 to the negative fifth X is equal to X squared. And just like we saw before, we can put this into quadratic form. And then again, if you want to do this by hand, you can. If you prefer to use a quadratic formula calculator, I mean, we're doing everything online here. You have a computer in front of you, so you might as well use one. Okay, and just like before, we wind up with two values for X. So X can be equal to 0.000242, or it could be equal to negative 0.000260. And like we said before, we can't have a negative concentration. So the value that has a negative sign is going to be ruled out here. And this tells us that if X is equal to 0.000242, okay, that's going to be equal to our concentration of hydroxide. So we have a POH that's going to be equal to the negative log of 0.000242, and I wind up with 3.62. Okay, that's our POH, and we have to remember that pH can be calculated from that, so 14 minus the POH, which was 3.62, and we wind up with a pH of 10.38, and that's our answer. Okay, which makes sense because it's on the basic side of the pH scale, and we're talking about a basic solution. Now, one last thing I want to mention here in this video is the relationship between Ka and Kb, okay, for a given substance. So if I have a compound that is a weak acid, okay, I know that if I add that to water, I wind up with an equilibrium where I produce hydronium plus the conjugate base. Okay, and I know that the Ka for this process is equal to the concentration of hydronium times the concentration of the conjugate base divided by the original concentration of the equilibrium concentration of the acid. But if I were to look at this base here and imagine what would happen if I added that to water, okay, I would produce hydroxide plus the conjugate acid. Okay, and we could describe the Kb for this process as being equal to the concentration of hydroxide times the concentration of the acid divided by the concentration of that base. Now notice what happens if I take Ka and multiply that by Kb. Okay, so that's going to be H3O plus times the concentration of 8 minus divided by the concentration of HA times the concentration of hydroxide times the concentration of HA divided by the concentration of A minus. Okay, and what you notice here is that A minuses cancel, HA's cancel, and what we're left with is the concentration of H3O times the concentration of hydroxide, which is equal to Kw. Okay, so for a substance, the Ka of the acid form times the Kb of its conjugate base will equal Kw. And the reason why this is helpful is, let's say you have a substance like ammonia. Okay, and we know that the Kb for ammonia is going to be equal to 1.8 times 10 to the negative fifth. Okay, but let's say we want to know what the pKa of ammonium is. Well, Ka for ammonium is going to be equal to Kw divided by the Kb for ammonia. Oops, not 10 to the 7th, 10 to the negative 14th, divided by the 1.8 times 10 to the negative 5th. And we get 5.56 times 10 to the negative 10th.